Hello, my name is Juarez Monteiro, and today I will be discussing our research on self-supervised adversarial imitation learning, or SAIL. At its core, SAIL addresses challenges in imitation learning from observation, a subset of imitation learning where we teach an agent to mimic expert behavior without having the labels that correspond to its actions. It's important to mention that this research was conducted through collaboration between me and my colleagues, as presented in this slide. The corresponding paper for this presentation will be available in the proceedings of the 2023 International Joint Conference on Neural Networks. As an overview, imitation learning is an artificial intelligence subarea that seeks to learn a given task with the help of an expert. The concept of learning through observation is something humans have engaged in since early childhood and can be applied to various learning scenarios. There are various definitions of imitation learning and its objectives. For instance, imitation learning algorithms learn by imitating experts to perform specific tasks like them. These algorithms observe experts and replicate their actions in order to acquire skills for specific tasks. The aim of imitation learning is to develop algorithms that imitate expert behavior, enabling successful completion of specific tasks. So, what if we can learn just by observing? Our research follows the concept of imitation learning from observation, where we learn from experts' experiences without necessarily having explicit labels for their actions. By following this concept, we can explore various sources to learn how to imitate. For example, we can learn from YouTube videos when we don't have direct access to the teacher's actions. SAIL is composed of 4 different models. A model which predicts an action given a state transition, presented in yellow box, a policy model, green box, a generative model, purple box, and a discriminator model, orange box. This setup allows us to overcome some of the traditional limitations found in behavior cloning. The first step, indicated by the red arrow, is to collect the state transition ST and ST+1 and the action A. For this, we first initialize our 4 models with random weights. With the policy randomly initialized, we can use this model as a random agent and collect all samples required to start our approach. The second step is to use the state transition and the action collected to train our inverse dynamic model in a supervised manner to learn the state transition function. In this step, we are going to use our trained model to pseudo-rotulate the trajectories from our experts, generating our pseudo-labels, what we call a hat. After creating all self-supervised labels, we train our policy, green square, using a behavior cloning approach. Unlike other behavioral cloning approaches, SAIL also uses a generative model, G, at purple box, to predict its next state, conditioned by the action predicted by policy. Hence, it also updates the generative model during policy training. Afterwards, SAIL uses the policy to create new samples that might help IDM, at yellow box, better approximate the unknown ground truth actions from tau E, the expert trajectories. Then, we use the trained policy to deliberate in a given environment, generating new data. Finally, SAIL appends all samples that the discriminator could not differentiate between the experts and the generated. The updates from the discriminator are backpropagated to the policy, which leads to local modification in its trajectories. We aim to discard trajectories that could result in the IDM getting stuck in bad local minima and update policy to correct some behaviors that the discriminator uses to differentiate between teacher and student. SAIL repeats all these steps for a specific amount of epochs or until both models stop improving. In order to measure our experiments, we are going to use 2 different metrics, the average episodic reward, and the performance, which is the average reward for each episode scaled from 0 to 1, where 0 is the random policy reward and 1 the experts. We are going to conduct our experiments using 4 different environments to test and compare our model. Cart poll, proposed by Barto et al., consists of a pole attached by an unactuated joint to a cart. The goal here is to achieve AER greater than 195 over 100 runs. We can use 2 actions to control the cart, push left and push right. Proposed by Moore, mountain car consists of 2 mountains, a flag and a car. The goal is to reach the flag with the cart and you have 3 actions for it, doing nothing, push to left or push to right. Acrobat, which was proposed by Sutton and Gerenford, consists of 2 joints and 2 links. The goal here is reaching the line using just 3 available actions, doing nothing, push to left or push to right. Proposed by Klimov, lunar lander consists of a robot and uneven terrain and 2 flags. The goal is to land a robot on the moon under low gravity conditions between 2 flags. The available actions are do nothing, activate the left engine, the main engine, or the right engine. For the expert samples, we train a different set of agents, mainly DKN and PPO. We define optimality in these environments as a threshold in the accumulated reward over 100 episodes. The results demonstrate the performance of the baselines and our proposed method, using 4 different environments. In most environments, cart pole, mountain car, and acrobat, SEO performance closely aligns with the teacher's reward. However, it performs comparatively worse in the lunar lander environment, resulting in the best overall algorithm across all environments. Comparing SEO to other methods, we observed a lower standard deviation in the first 3 environments, but a higher deviation in lunar lander. We attribute these lower deviations to the gradient flow from the discriminator into the policy, and the intrinsic encoding of each environment's physics in the generative model. We have a deeper discussion about the results in our paper. By properly encoding physics into its policy, SEO achieves a behavior that helps the agent produce similar results to the teacher, leveraging its knowledge of how ST+1 should be given the action and the ST. The study reveals that SEO inherits from different behaviors from behavioral cloning methods. Initially, it necessitates a larger sample size than a single trajectory to match its teacher's performance, as a single trajectory offers inadequate data for SEO to accurately encode varying states and significantly generalize within each environment. Secondly, SEO suffers from the inability to scale according to the sample size due to the issue of compounding error, leading to decreased agent performance as a policy deviation from observed trajectories lessens with increasing samples. However, as demonstrated in this table, SEO attains near-perfect performance with just 25 episodes, though the standard deviation decreases consecutively per row before increasing again with 100 trajectories. The study hypothesizes that these results are achieved via the updates from the generator and the discriminator models, and by adopting a different objective, such as replicating trajectories closer to the teachers, which reduces the dependence of the policy on its LFO objective and requires fewer episodes than previous methods. Nevertheless, the success of SEO is also attributed to its smaller discriminator model, which is sequential and hence limits the sample size. Therefore, it cannot utilize larger sequence models such as transformers due to the risk of overfitting the model to a smaller dataset because of a high number of parameters. Increasing SEO efficiency may need more experimental exploration about augmenting the observations, since modifying teacher samples to avoid generating impossible or undesired transitions necessitates prior domain knowledge. In this paper, we developed a novel LFO approach that uses an adversarial model to learn how to imitate the behavior of teachers without accessing its actions, and it's capable of achieving state-of-the-art results in performance and efficiency. We evaluate our model under different amounts of sample behavior and compare it with various baselines from the literature. SAIL achieves significant results in both performance and AER with fewer samples. We believe that reproducibility is a practice that we all need to work together to have a community that keeps evolving. In order to reproduce our work, we let all codes that we use in this paper available at this link presented in this slide. I also would like to thank that this work was supported by UK Research and Innovation in the UKRI Centre for Doctoral Training in Safe and Trusted Artificial Intelligence. That's it. If you have any doubts, don't hesitate to contact one of the listed authors. Thank you for your attention.